Stanford University.
Okay. Welcome. Sorry for the technical difficulties. EE380, my name is Andy Freeman, spring quarter 2009-2010. Many people observe the world and try to predict things that are going to happen. The old model for doing so was essentially curve fitting. Take some measurements, guess what a curve might look like, try to predict some observations. And the cool thing about it was that it worked regardless of the domain. You just sort of said cubic, whatever, and thanks to some nice bit of mathematics, you got a result. Had another nice property, it had low computational requirements, or at least relatively low. However, we don't live in that world anymore because we don't care so much about computational requirements. As a result, we can start to do things like introduce relevant theory. For example, snow, which is one of the important things for today's talk, has physical properties. It has heat capacity. We have theories about how snow works. We have theories about how water is absorbed into the ground and other sorts of things. In some sense, we can run simulations of mountain ranges, because it turns out mountain ranges are just as susceptible to theory and simulation as circuits and other things we might consider as computer scientists. Today's speaker, Jeff Dozier, has been applying computation to geophysical problems, especially with respect to runoff. Thank you.
Okay. I'm not used to seeing myself when I lecture. So,
put the jacket, don't worry.
So in periods when we're concerned about climate change, one of the things, of course, that we're concerned about are the effects on water. And, oh, there we go. And so perhaps the most important question for this future is the first one that we list here. That is, in a time when climate is changing and populations are changing and land use is changing, how can we protect the ecosystems and better manage and provide water of appropriate quality? And if we sort of translate this question into a question about the mountain snowpack, the one we ask is, how can feasible improvements in our knowledge about the mountain snowpack lead to beneficial decisions about water, both for human uses and for ecosystems? So this is a view of the hydrologic cycle that is perhaps a little bit different than we normally see in hydrology textbooks, emphasizing that much of the cycle is in fact engineered. The snowpack is not engineered very much, except perhaps in areas where we do avalanche control. But downstream of the snowpack, it goes through forests, which are managed. And in fact, in some universities in this country, departments or schools of forestry are now called schools of forest engineering. It goes into agriculture, where we're we're transpiring the water and adding chemicals, and it goes into the urban and industrial environment, and including in energy production, where the consumptive use of water for energy production is about 20% of the non-agricultural use. And so when you when you run your appliances in your house, you're actually using as much water as you are taking showers and watering your lawn. So in the snowpack, there's some characteristics that we normally think of. So this is a snow pillow at Levitt Lake in the Walker River drainage, just over the ridge from the Tuolumne. This shows the amount of snow on the pillow in water equivalent, and this is a pretty heavy snowpack. It's 2.5 meters of water equivalent in 2006, and in 2007 it was a drier year. And what we see, and what the graphs on the right show for the 2 years, is the snow pillow is measuring the total amount of snow that's sitting there. And what I've done is taken the daily derivatives and translated the positive ones into events that represent snowfall, and the negative ones as events that represent snow melt. And this is what we normally think of when we think of the mountain snowpack, that it accumulates this water over a period of 5 months or so, and then it releases it in the spring and early summer, right as the agricultural demand is increasing. So in effect, the snowpack acts as a reservoir that hangs onto the water until we really need it. And this is what a snow pillow looks like. It's a stainless steel sandwich filled with antifreeze, and they simply measure the pressure on that water and therefore estimate the weight of the overlying snow. Now, if we look at a snow pillow at a lower elevation in the same drainage, this one, notice that the vertical axis on the snow water equivalent is a lot smaller, going only up to 800 millimeters. And also what we're seeing, if we look at the daily derivatives, is we're seeing some midwinter melt events, and we're also seeing an earlier initiation of runoff. And of course, one of the things we're worried about in a climate with warmer temperatures is whether these kinds of effects that we're seeing at the lower elevations are going to translate into higher elevations. So one thing we think about the snow is what we just said, that it hangs onto the water until the spring. But there's another aspect of snow that is important, and that is that it gets moved around by the wind. And so we have a lot of spatial heterogeneity within scales of a few hundred meters. So this is a picture taken up at the Reynolds Creek Experimental Watershed in Idaho. You can see a fence in the background there. And so the snow in the foreground is only a half a meter deep or so. And yet in the back where those trees are, the snow is about 4 meters deep. And so the trees, they've figured out where the snow is going to accumulate, and they've decided that that's the best place to grow. So the two important things about this heterogeneity that you probably don't think of is, one is that when snow melts, it melts from the top. And so the heterogeneity smooths out the rate at which this meltwater arrives at the soil surface, and therefore smooths the hydrograph. And secondly, the snow where it's piled deeper persists longer in the season and provides zones of increased soil moisture. And so if we transition this kind of an area to a more of a rain climate, we're not only going to make the water disappear earlier, but we're going to eliminate a lot of this heterogeneity. Okay, so that's the part of the talk that is the snowmelt runoff. As you recall, the title is the Snowmelt Runoff, the Fourth Paradigm, and the End of Stationarity. And I'm explaining what those things mean. So to this audience, I don't have to explain who Jim Gray was. Most of you have read a lot of his work. When I speak to earth scientists, I have to explain that Jim made possible ATM transactions, and therefore you're all grateful to him. And Jim, of course, was lost at sea 3 years ago, but only a few weeks before he was lost, he gave a lecture at the National Academy of Sciences in which he articulated this idea of a fourth paradigm in science, which is very data-intensive science. And this talk was, in fact, recorded and transcribed. And in this book, which is available through the Creative Commons license, the introductory chapter is, in fact, an edited version of the talk that Jim gave. And so the idea of what he called the fourth paradigm of science, built on the previous three paradigms. That is, if we go back to the Greeks, science was largely experimental with descriptions of natural phenomena. And then a few hundred years ago, the heroes that we study when we take high school physics emerged, people like Newton and Maxwell. And then the third paradigm was really something that started, in the 1960s, where the simulation of very complex phenomena and coupled equations with computers. And what Jim articulated was that today we're emerging into a fourth paradigm, building on the other three, in which the science is very data intensive, and that the questions we answer often require going through not only large volumes of data, but lots of complex data types. And then in the fourth paradigm, there's a chapter that Bill Gale and I wrote that described what we call this emerging science of applications. That if we look at universities, in the previous 100 years, they're very discipline-oriented, with divided into departments of geology and physics and chemistry, and some universities are kind of like that today. But beginning in the 1980s, with a report that Francis Bretherton helped write, we began to see earth science as a single complex system. And that is, you can't study biology without studying the climate, and you can't really study the climate without studying the biology. Tom Dunn and I teach a course in this, and our principle that we explain to the students at the start is, you live on a planet, and therefore it's good to know a little bit about how the planet works. And of course that means that it is, we work at large scales, and it is in fact data intensive. And what is emerging today, we see, is knowledge that we need to target practical decisions. And if we apply that to the water cycle, this application science is need-driven instead of necessarily curiosity-driven. That is, we have problems that society faces that we have to solve. It's externally constrained by events. So if you come from the eastern United States, which I'm sure some of you do, your wastewater treatment systems there were built about 100 years ago with about a 100-year design lifetime. And so therefore, the time to sort of solve some of those problems has to be now, because otherwise those systems are starting to fail. Useful even when incomplete. My next topic I'll say something about is what we're calling the end of stationarity, and that is that many of our statistical relationships that have built up over the years, we've now discovered have applied to a situation that is changing out from under us. And what that means is that if we keep doing water forecasting the way that we've been doing it, not only will we just continue with the same dismal performance that we have, but we'll actually get worse. And so, therefore, we have to do something better, even if we don't completely understand just what we have to do. Consequential and recursive, things like ethanol for corn-based ethanol production has huge implications for water. Scalable, at the plot scale, we sort of understand, I think, how the carbon cycle works, but not at the continental scale. Robust, in that we have to sometimes express caveats to decision makers in ways that they don't quite understand. And also data intensive. And again, I would say not so much the data volumes that are unmanageable, but the things that are hard to manage are the complexity and the number of data sets. And as Stephen Chu has said, a former faculty member here at Stanford and then director of the Lawrence Berkeley Laboratory and now Secretary of Energy, said, we seek solutions, we don't seek, dare I say this, just scientific papers anymore. Okay, the whole issue with stationarity is, in addition to the snow pillows, there's another way that we've been measuring snow for which the record is longer, and that is starting in 1910, Professor James Church at the University of Nevada, Reno, developed this method of plunging a coring tool into the snowpack, pulling up the core and then weighing it and subtracting the weight of the tube and therefore estimating the weight of the snow and therefore the amount of water in the snow. And his first snow course, established in 1910, was out Mount Rose, just outside of Reno. And we still call this tool the Mount Rose snow sampler. And so a variety of agencies participate in making these measurements. And some of these are made in the wilderness areas by people, spending the winter going in on skis every month. And so these jobs have very little turnover because you get paid to backcountry ski. So if we take a snow course at one of the lower elevations, and this is the Rubicon Valley snow course in the American River drainage, the top graph shows the time series. Notice it wasn't continuous. There was a gap in the 1950s when the course wasn't operated. And then if we normalize these data, now they typically don't have normal distributions, and so what I usually find is the generalized extreme value distribution works, but there's a way of normalizing that in a way that's similar to a z-score. And what we see, and this is typical of many of the stations, particularly at the lower elevations, is that there's in fact a trend in these data over time. And that is, if we take all of the stations that have a long-term record, and what I defined as long-term in this case is more than 50 years of data and continuing to the present. That didn't stop somewhere in the past. And then if I do that calculation of the slope of that line as to, and with the normalized values, so I'm calculating the slope in terms of the sigma values per decade, and then I color code those. So these are all the 220 stations that are long-term, and the big red circles are those that are declining at more than 0.2 of a standard deviation per decade. The squares are between 0.2 and 0.1, and the red circles are between minus 0.1 and minus 0.05. And the blue ones are ones where we see a slight positive trend over the decade. And then this line represents, notice, elevation on the left hand, on the vertical axis, and latitude on the horizontal axis. And what we see is that depending upon your latitude, all of the stations that are declining are below that line. And most of the stations that are having accumulation are above that line. And so the consequence of that is that the snowpack is shifting over the time period. And so therefore, statistical relationships, well, the way these data are used is to forecast the spring runoff. And one of the forecasts is to try to estimate the total runoff, the April through July runoff. And and these are really just based on multiple regression equations with the data at the snow courses. And so if we look at our performance in doing this at the American River, for example, the horizontal axis is the absolute error, and the vertical axis is the cumulative distribution function. And so if we take the median on the vertical axis, the 50th percentile, we see that our median error is 20% of the runoff. And if we go up to the 80th percentile on the on the vertical axis, we see that the error is on the order of 40% of the runoff. So if you subtract 80% from 100, that means that 20% of the time you've got an error that exceeds 40%. All right? And so the forecasts, therefore, that are issued tend to have a lot of error. So this is the one that was just issued in Bulletin 120 from the California Department of Water Resources. It says, you know, this year we're expecting a little bit over 1,000 acre-feet of water, which is about 85% of average. The average is 1,240, remembering that this is not a normal distribution, but this is a government agency. And notice that the 80% probability range of the forecast is pretty large. It goes from 770 to 1,700. And so, and because of the way the snowpack is changing, if we keep using this method, the performance is going to get worse. And it's not very good now. In other words, when you think of what we're trying to do with this reservoir, it's got 5 purposes that I can kind of enumerate off the top of my head. One is it's for flood control. Second, it's to provide water resources. And if you think of just those two, they're diametrically opposed to one another. For flood control, you want to keep it as empty as possible. It provides hydropower, it provides recreation, and it provides services to downstream habitats through things like river restoration and aquatic species and things like that. And so, in order to sort of properly manage amongst these competing purposes, it really helps if you had if you could sort of tighten this probability range a bit. Yeah?
So basically what you're saying is that the current process operates by analysis of a time series of historical data.
It uses a statistical relationship which is derived from a time series of historical data.
Essentially the same thing, I think.
And the fact is that it isn't stationary.
And going back to the distribution, the figures you just had, the error bounds are not symmetric at all. So the estimate is sort of 300.
Well, it's a heavy tail distribution.
Right.
So you wouldn't expect the error bounds necessarily to be symmetric about the expected value. Yeah. Okay, so this is just a repeat of what I just said, that these empirical methods, if we look at the second bullet, were developed over a period when the human impacts were more isolated and we think the pace of climate change was slower. And this paper by Chris Milley and his colleagues in Science a couple of years ago, the idea that stationarity is dead. And so therefore, if we're going to be able to make sort of logical decisions, of adaptation versus mitigation, that we need to have methods that are more physical and less empirical. And so how do we do this? How do we approach doing something new? Well, so philosophically, the way I've tried this graph out on people, and sometimes it works and sometimes it doesn't. So this is, the bottom graph is the investment in science on the horizontal axis, and the return, the marginal return on the, d science, d dollar on the vertical axis. And then the top one is just the integral of the lower one. And this is conceptual. There are no numbers on either axis, and that's meant to be. Okay. And the idea on this is that when you start out in a branch of science, something that's new, initially the marginal return of the investment is low because people are working in isolation. And then your marginal return starts to climb because you build a community and we stand on each other's shoulders. And eventually, though, that marginal return peaks, and then it starts to drop. It still is significant, that is, the integral still keeps climbing. But you do eventually get to a point where the problems that are both important and tractable have been picked off. And we're increasingly left with working with problems that are either really, really hard or not very important. And so one of the questions when we're making investment in science is to say, well, what ought we to do to sort of kick this marginal return up again? What investments ought we to make to do something different? And my thesis is that we don't use each other's data very well. And so if I look at data, what we see is that there's sort of increasing value of data as we go up this ladder, but that as we get further up the ladder, we do a poorer job of making that information available. So if we look at what we might call the raw data, the precipitation measurements, the river gauge measurements, and things like that, those are pretty easy to obtain. You can, most of the agencies, I think, do a credible job of doing it. In many cases, the measurement technology is reasonably well developed, and the internet has certainly made distribution easier. But as we go into aggregating to higher level products, I think we find that this is not the case. And so my colleague Jim Frew at UC Santa Barbara has come up with this diagram of what we call the data cycle, in which we go through this process of collection, storage, search, retrieval, and analysis, presentation. But the idea is that the data cycle loops back on itself. And so data that one scientist produces should be something that is in the collection phase for the next investigation. And so we can think of sort of different categories of science information people, from those who are users of the information, who want reliable, timely information products, the funding agencies, and then the idea that there are science information authors who would like to help users, but have the requirement for transparency and the ability to distribute. Yeah.
Yeah. A couple of years, about a year ago, a little more than that, Professor Laughlin from the physics department talked about this to some extent. And it was his observation that substantial quantities of data, information, raw information, or partially processed information is being tied up as proprietary information by various organizations, companies, and the like, and that in fact that was beginning to impact what we could do in terms of predictions and understanding of scientific problems. Is this something that you see in the water area?
Yes. To some degrees more than others. One of the problems in working internationally is that foreign water data are often very hard to find. And are treated as sort of national security information by the countries involved. So when I was working in Tibet, as we discussed, I could go look at a book that had the data. Okay.
Can't you get that data from satellites, whatever?
You can't get water stage data from
Yes,
satellite.
you can. Differential SAR.
Well, we're looking at, there is a mission proposed, the SWOT, the Surface Water and Ocean.
You found people using too much water locally.
You can't get it all from satellite, unfortunately.
Well, at least something.
And that's one of the advantages of satellites, is that you do. But let me talk about some of the difficulties with the satellite data. So the idea of what we're thinking of is that there are these progressive levels of data, and this idea really came out of the Earth observing system. The raw data from the instruments are often hard to use, and in the case of social science data, sometimes not available for reasons of confidentiality. So for example, you can get to the raw census data 72 years after the census is taken. But what is available is something that is processed to higher levels of information, and then we're thinking of these higher levels of data where they're geospatially organized, they're interpolated, or they may be synthesized from several instruments. And then some requirements that I think are needed are peer review is still useful. That is, if you simply look at information that is widely available on the internet, you wish much of it had been peer reviewed. So the idea that if you have confidence in data, you want to know that there's a chain of validation. That you also want to keep track of the provenance of the information. So if you have a number that I've produced, you'd like to see how that was produced. That there is some theoretical or empirical basis for the algorithm. And then there's the issue of availability. And our idea is that we ought to use the DOI. And so if there's a data set that a paper is used, there would be a DOI citation to the data, and you would be able to retrieve that. Let me give an example to, I think, show why this is necessary. So this is a data product that my students and I have developed and produce, and it's the idea of fractional snow-covered area. And the idea is the instrument, in this case MODIS, has a pixel size of 500 meters at nadir. And the problem is, and it's available daily, but the problem is at 500 meters is there's variability within the pixel. And so we have a method of coming up with what we call the fractional snow cover within the pixel. And that product is shown on the right. So it uses this image in the middle to produce the image on the right. And the one on the left is just showing the topography of the Sierra Nevada. Now, okay, and the way we can do this is that different components of Earth's surface have different spectral features. And so, for example, vegetation, typically it's dark in the visible part of the spectrum. It's brighter in the near infrared and tails off. Soils tend to have bright reflectance pretty much throughout the spectrum, a little bit darker in the visible. Snow has a reflectance that varies with the grain size. But in the visible part of the spectrum, it all looks white. So it's interesting that snow is in fact one of the most colorful substances in nature, except that most of that variability in color is out beyond the visible wavelengths. And what we see if we take a typical spectrum from each of those three graphs and then superimpose the particular satellite instrument's band passes on it, we see that snow is in fact one of the few substances in nature that is very bright in the visible part of the spectrum and pretty dark in the near infrared part of the spectrum. So and this is just an illustration of what you can see if you if you look at the left-hand image from the Landsat satellite. The left-hand one is a visible image, and you can see that the snow and the clouds are pretty hard to discriminate because they are, in fact, pretty similar. It's the same multiple scattering process, whereas the difference between snow and cloud is that in clouds, the scatterers are a lot smaller. And so if we go out to the near-infrared part of the spectrum where ice is more absorptive, it makes it darker, and we can see that it's very colorful. So in fact, if your eyes were sensitive out here, there would be a tourist industry of, sort of like the leaf peepers in New England, going out and looking at, the colors of snow as they change through the season and had spatial variability. Okay, so the computational parts of the problem are formidable but not impossible, and that's why we're able to do this. So the idea is that for each pixel we have a set of reflectance values that's on the left that we can measure, and then that we have a combination of n members that have particular reflectances in each of the band, except the snow's reflectance varies both with the size of the grain and also with the contaminant amount. And then we have other n members of the pixel. And then we linearly combine them with the fraction of each of those n members. And then there's some sort of an error term. And so the idea in this is that you can solve for that vector of f values. And constrained by each of them has to be positive, and they have to sum to 1. And we do this in a least square sense and minimize the error term. Now, the problem is we have to try this for various vegetation end members, various soils, and various kinds of snow. And so there's about 600 combinations that we have to try, and then we pick the one that has the least squares minimum. So there is some heavy computation involved because we're trying to do this for every pixel. Yeah.
So you have a geographic constraint here, though. Each pixel comes from a fixed spot on the Earth.
Yes.
You do that historically. You track through the year, and then use those comparisons to determine changes from vegetation to soil or whatever.
We're taking the view that the reflectance of the vegetation is changing seasonally but not daily. And so there's still some issues of how to constrain the search space in one of the ways we're trying this is we sort of have an idea of knowing which combinations are close neighbors of one another. And so in the search space, you can search in the neighborhood and you don't have to go necessarily too far outside it. So the idea, though, is we take the MODIS image and then we can come up with a map of the n members for each of the elements. Okay, now there's some other issues. We get daily data from MODIS, but we're getting this from a 700 kilometer orbit altitude. And so in order to get daily coverage, it means that on some days you're looking pretty far off nadir. So the left-hand image at the bottom is on the 8th of April, 2004. The right-hand image is on the 9th of April. And what you see in the right-hand image is it's blurrier. And particularly it's blurred more in the east-west direction. And the reason for that is that if we look at the top, these are the viewing angles for each of the images. And the left-hand image is pretty much, within 8 degrees of nadir. The right-hand image is more than 50 degrees off nadir. And in fact, the fact that there's 2 histograms, it means that this image was in fact pieced together from 2 separate orbits. So, and we also have missing data because of cloud cover, sensor outages, and things like that. And so what I do on this is take advantage of the fact that we have daily coverage and do a smoothing spline interpolation between them. And the way I weight the spline coefficients is inversely with that viewing angle. So in fact, I calculate what at the edge of the scan, the pixel is about 10 times as large as it is at nadir, when you go 65 degrees off nadir. So what I do is to weight the spline inversely with that viewing angle. So if in a period of cloud cover, I've only got one shot and it's an off angle, well, I'll use it. But on the other hand, if I have a lot of coverage, then that off angle shot gets very little weight. And so therefore we can put together and this is for a single pixel. The left-hand side is at a high elevation one and the right-hand side is a lower elevation one. So the left-hand side, the one at 3,500 meters, we're seeing, pretty continuous snow cover. And then notice that the pixel, that it doesn't just fall off, that it slopes, the coverage of the pixel slopes downward, and that's because of the heterogeneity within the pixel. And in fact, I think we can recover that heterogeneity. Whereas on the right-hand side, we're seeing intermittence. We see times during the season when the snow cover completely disappears. And we can also get at the grain size of that snow, and we see the storms coming that kind of refresh the grain size. And then from that, we can get the reflectance. So this is what the model structure looks like, and this is what I meant. We said, well, we got to bring a bunch of data sets. So we have a cloud mask, we have the MODIS data in 7 bands, we've got some quality flags that go along with it, we have a map of the viewing angles, and we have a map of the solar angles that go along with those. And what we produce are mainly the snow fraction and the albedo, the reflectance, but we also produce images of the error, the vegetation fraction, the soil, and so forth.
For every pixel.
For every pixel for every day. All right. So in terms of data volumes, you're keeping track of a lot of data, but it's not huge. To do it for the Sierra Nevada, the input data is about 36 megabytes a day, which, that used to be a lot. It's not. And if we look at, if we tried to expand this to the snow-covered areas around the world, that number goes up to about 8 gigabytes. And then the products we produce are about 10 megabytes per day. And there's a lot of things we do. Obviously, we try to use a database to keep track of all these things. So if I want the images for a particular day, for a particular input value, I can find somewhere on the file system where that is with the database. But it turns out that embedding that information in the file name is also a very useful cross-check, because it allows you to crawl through the file system and build the database. It turns out if you have a table in the database that supposedly reflects the things that are out on the file system, it's a little too easy for those to get out of sync. And so having a way of doing it, of not losing that information by Essentially, we use the Napster model for doing that. We just call it Modster, right? Okay, and so what we can do with this is we can estimate not only the progression of snow-covered area through the season that's shown in the top row, but we can also estimate the reflectance of that snow as it, because of these metamorphic processes and the contamination, it gets, two things happen as the snow goes through the season is the sun angle's getting higher, so you're getting more input solar radiation, and the snow is getting a little bit darker, and so you're absorbing more of that. And so, so what we can do with that is we can calculate the net solar radiation on the snow cover as it progresses through the season. So in addition to the snow cover, can I get to the amount of snow? Can I get a spatially distributed estimate of the snow water equivalent? So currently, there is no satellite that can do that directly at the scale in the mountain areas at the depths of snow that we experience. Out on the plains, you can use a passive microwave instrument, but that has, because in those wavelengths, the microwave emission is small, you have to have a big pixel to get enough photons, and also that only works up to about a half meter of snow water equivalent. So this is the American River showing the topography and showing the places where we have snow pillow measurements. And then this shows for 1 year, how each of those snow pillow measurements go up and go down during the season. Okay, so if you take those snow pillow measurements and you use your favorite GIS tool and you spatially interpolate between them, you'll spread snow well out into the Central Valley. All right, that's one problem. The second problem is late in the year, you'll find those snow pillows don't go to the highest elevations. And so you'll find that there's still a fair amount of snow in the watershed after the last snow pillow has melted out. And no interpolation method that I know, can take a bunch of zeros and produce something other than zero somewhere. So there's two approaches that we've used. So one is, the one thing you can do with the satellite data is I can constrain where that measurement goes to zero because I can tell where the edge of the snow cover is. A second thing I can do with those energy balance estimates is I know the date for every pixel when the snow cover goes away. And so if I can back calculate the amount of energy that it took, how long for that particular pixel at that particular orientation, how long it would take that snow cover to disappear, I can tell how much there was at the start. Now, the only problem is that's only a retrospective analysis. So one of the things I think we're interested in is how well do those two methods work? So if we look at the blue line here shows the interpolation from the pillows, and the red line shows the retrospective calculation. And then this is the total amount of snow in the basin in terms of cubic meters, right? So we actually now have an absolute estimate of the volume of water. And this graph looks pretty good. It looks deceptively good. Because the correspondence between the results is coming from canceling errors. So what we see is if we look at different elevation bands, then the results are not so good. In other words, what we're seeing is the reconstruction from the energy balance is producing more snow at the higher elevations, whereas the interpolation from the snow pillows is producing more snow at the lower elevations. And so one of the things we need to do is to try to resolve, what in fact is causing that change. Okay, and the idea that we'd like to be able to do this as we go into the future is that the future is a bit uncertain. If we look at what climate models are telling us, if we compare 15 models for the western part of the U.S., we see on the right-hand side that that those models agree with each other pretty well. And in terms of the past, they agree pretty well with observations. That is one of those lines that's, what the bar represents is the mean and the standard deviation amongst the 15 models. And so for temperature, they do pretty well. For precipitation, they don't. And so not only that, if we project those models into the future, into a doubled CO2 environment, what we see is that if we take the standard deviation of the model results around the mean for every month compared to the current value, we see that in every month except October, that range crosses 0. So what we don't know based on the models is whether a warmer future, we know the future is going to be warmer, but we don't know whether it's going to be wetter or drier. And so therefore, we have to do a better job of being able to keep track of what is actually happening. You were raising your hand?
Yeah, it's curious as to whether you have a hypothesis as to why this is the case. You're doing your analysis on a sort of two-dimensional model. Is it possibly a three-dimensional effect?
Well, there's a couple of things. One is it's the models tend to parameterize precipitation rather than going into the cloud to the processes themselves. The other is, of course, that chaos theory came out of an analysis of precipitation. That is, the Lorenzo's original paper was trying to simulate convective precipitation. And what he realized when he had to restart his computation because the machine went down, and he started it by typing in the numbers, but only to the precision that they were being displayed on the paper at that point. And he got a different result. And so he explored this, and what Phil Duffy has done. So one of the questions, are El Niños wet or dry in the western U.S., in California? And the answer is they're wet or dry. Well, but they're typically not in the middle. So we've had 6 strong El Niños, and 4 of them have been wet.
Doesn't that basically mean the variance goes up? You're getting more wet and more drier? Alternating, whatever.
That's certainly one of the things that
chaotic, if you would.
Yeah, that. In other words, yeah.
But that's a higher variance first of all.
Yeah. Well, and when Phil Duffy was trying to look at one of the dry El Niños, which was the 93 El Niño, he was able, by doing perturbing the input value, the noise in the input values, he got 2 dry ones and 10 wet ones. But nature gave us a dry one in that year. So, if we think about in terms of the climate science that we should be worrying about, there's an interesting essay by Schiermeier in Nature, is that these are the real uncertainties that we ought to think about. Regional climates, because that's where adaptation is going to occur, and there are problems with downscaling, especially in the mountains. And in fact, one of the issues is are the models getting the orographic effect correct? Because if they are, then you could say, well, a higher resolution model will give you better results. If they're not, then a higher resolution model is just solving the wrong equation more precisely. Okay. So precipitation is one of the big uncertainties. Regional climate, aerosols, we don't have many data. And then there's some interesting divergence from the record in some of the paleo data that needs to be resolved. Now, of course, when you read the popular press on the uncertainties in climate models, they're not discussing any of these. And of course, what Gavin Schmidt has said is that we're working in an insane climate of suspicion that is drowning our ability to soberly communicate what the real gaps are.
Couldn't tree rings help you in deciding what's happening in statistics on wet and dry?
Yeah, and what they show.
Increased variance of
Well, I don't know who's really done much on the increased variance.
You need more data.
Yeah, what the tree ring data show is that one is that we know is they clearly show persistence in the hydrologic cycle. That the wet years tend to occur together and the dry years tend to occur together. And droughts of 6 to 8 years in the 600-year record are not uncommon. The other thing, of course, though, you got to be a little careful with the tree rings, is that they are better at identifying dry periods than wet ones, because you can, with tree rings, get to enough water where the growth is no longer water limited. So you may not be able to tell the really wet years based on the tree ring data. The other issue, and it gets to, is the limits of predictability. So the common question that people ask about any, sea level or water or temperature is, what's the worst case scenario that we're going to expect at the end of the century? And it turns out that's a very hard question to answer, because in order to really get that answer, you have to not only have a model that you trust, but you also have to know what the statistical distributions of all the input variables are. And so it turns out that's hard. And part of the issue is that, we tend to really want to make predictions. And so the success in numerical weather forecasting has kind of led us into this trap of saying, well, the climate models, if they were better, would tell us more precisely what things would be like a half century from now. And part of, I guess, my thought about the way we manage the snow cover is there's lots of things we can do that help us in the short term as well as the long term. And because, again, part of the climate debate is that many of the mitigation measures will only benefit some time from now, whereas the same kinds of tools that help us deal with variability will also help us deal with change. And there's an essay by Daniel Sarowitz in a recent issue of Nature that is worth reading, because he he looked at the analogy with earthquake prediction. And many of you probably remember that a couple of decades ago, there was a lot of focus on short-term earthquake prediction. Could we have a prediction that would, like a landfall of a hurricane? And what Sarowitz's point is that earthquake science became really societally useful when they realized they couldn't do that. And instead, what earthquake science has given us is sort of logical statistical distributions of magnitude of shaking, and the societal response has been an improved building codes. At UC Santa Barbara, and I would guess here, if you move into a new office, you got about 2 weeks to decide where your furniture is, and then there's a guy's going to come around with a drill and a bunch of bolts and say, this is where it's going to be. And any planning evacuation routes in the case of a disaster, rather than focusing on the short-term prediction problem. And so it's an essay that I recommend to everyone.
Going back to your earlier talk about data and how it gets distributed, is there an advantage? Does anyone actually taking and doing modeling based on a large percentage of the available data rather than looking at small pieces of it?
Well, I guess I'm going to answer a different question. Okay, that's my prerogative, right? Part of the issue is that in producing something like this snow cover product or many other products, there's a lot of arcane knowledge that you need in order to do this. And so if you're interested in doing hydrologic modeling based on snow, you don't want to start with the MODIS satellite data, because you and your students have a steep learning curve that you have to climb if you do that. And so there's a better solution, is you ought to be able to get those analyses from somebody else. And you can get them from me, although the mechanism is still pretty primitive. You send me an email, I send you an FTP address, we correspond about it, and you can get the data, and we have a bunch of people that are doing that. It's not a very good mechanism. I ought to just be able to publish a DOI, and you can go there and find the data, and that should be persistent. It should take care of issues of provenance. If there are two data sets that are similar but different, you should be able to see what the explanations are. And that's the way I think we make progress in, while I'm messing around with the remote sensing aspect of this, others can be using them in runoff models. So, if you want data, see me. Okay, thanks very much. Right.
Questions?
Since you have a computer science group, they know all about Google, as they know about your domain. But, so let me ask the stupid question. Why not send all your data to Google? They know how to manage large data. You can tell them how you want to do it. You can train so that people, interactions, whatever. But at least it gets the bit out of your hair.
Well,
and the communication part, then you get the nice displays and whatever.
Yeah, the issue is a couple of things. One is, I don't know that they figured out how to handle space-time data.
You have to tell them.
Well,
they're pretty smart. They learn.
Yeah, they're
The first version may not be what you want.
Okay.
They're pretty smart, they learn.
Sorry?
They're pretty smart, they learn.
They have machine learning algorithms.
Yeah.
Pretty smart,
Yeah.
they don't learn. That's the whole point of being
Okay,
smart.
fine. And start your Google too.
Well, and then the second
No,
issue
it's
is,
just the print,
yeah,
forget about Google per se. Finally, you can send it to Microsoft.
Yeah.
No, sorry.
Well, no.
No, just Some generic.
Well, I think one of the things we're all thinking about, at least in my field, is a term we're using, we're sort of calling graduated outsourcing. Because, for now, for example, putting my data on the Amazon Web Services is still not cost effective. But I don't think that's going to be true forever. It's still, at this point, cheaper for me to buy disks than to store it at AWS. Part of the challenge that we have as earth scientists is kind of keeping track of what the industry is doing, having some idea of what things that you're doing are likely to appear in the future. But one of the problems that I think has occurred in putting together these large data systems is not being adaptive to the changing technology. And so there's a question of, how do we tune ourselves so that we don't, NASA's Earth Science Information System, well, kind of while it was in development, the web came along.
Came and went.
And so things happen within the generation of a procurement cycle that.
Well, the LHC has set up an enormous data distribution network, which is significantly higher data volumes than you can manage on the internet. There are initiatives on the internet to build essentially server farms for holding large quantities of data. And of course, the storage cost of large quantities of data is dropping rather rapidly at zero. I've seen $3,000 machines that have half a petabyte of disk on them. And that's fairly impressive.
Yeah. Transmission is still, Jim Gray, one of his papers was that at some data transfer rate, I think his example was a terabyte, that FedEx was your fastest bandwidth.
You start filling up a shuttle with tapes was faster.
Walkman, always faster.
Yeah.
Yeah, but you're not talking about quantity data yet, are you?
Yeah. No, like I said, the reason, part of this is of interest is that it's mainly spatial data tend to be big, bad, and ugly in that they do have large volumes, but not as, like the National Ignition Facility generates a terabyte of data in some number of nanoseconds. They have complexity. That is their, like when you take drainage basin boundaries and fit them together, they don't, you end up with holes in the middle, for example. So they tend to stress data systems, but not to the point of unmanageability. So like I said, they're problems that are hard, but they're not intractable.
What's the granularity size for information in, say, the field that you're working in right now, snow cover? Is it 100 meters, 10 meters, 1 meter?
Well, there's a trade-off between your temporal resolution and your spatial resolution. So if you just think of data rates, well, your data rate coming from the instrument is your spacecraft velocity, which is fixed by orbital mechanics, times your swath width, times the number of bands you have, times the number of bits per band, divided by the square of the resolution. okay? And so so there's a trade space that you can work with. So now, you
That's
know,
the data acquisition side. But in your modeling side, how big a cell do you want to model in order to
that's
look at the
interesting.
data?
Okay.
That's the other side of things. If you're going to do the fourth paradigm hack,
Yeah.
on one side you've got data, and the other side you've got model. How big is the model?
Okay, so I think there's an interesting question that, first of all, a lot of times the models are just driven by the data, but how do we treat heterogeneity in models? We resolve it out. Yeah, no, we squeeze the model time step and space grid to the point where if it's a coupled differential equation, at every time step, every variable in every cell has a value. And one question is that the right way to do things? I mean, it may well be that what you want instead is a statistical distribution of each value. And if you have a statistical distribution that's not just empirical, then there are some things you can do analytically as you propagate those together. And so, one of the ways, if we think of the way what do we do with an increase in computing power? Well, there's sort of three axes. You can squeeze the resolution, which is typically what we do. You can run it over longer time periods or more parameter space, which is, do you know about climateprediction.net? Well, it's a PC climate model, and it uses the BOINC software out of the Berkeley Open Infrastructure for Network Computing. It's like SETI at home, and so you can kind of explore the parameter space, or you can do it by changing model complexity. And for some of these problems, I think that model complexity axis is something that we need to think about. So, yeah.
So you said you've got this data and you're sort of distributing it by email.
Well, by FTP is what
But if I knew something about the field and had a crazy idea and came to you for data, do you have a meta description of this stuff that I could just sort of read from the web page and understand it all, or would I have to interact with you to?
You'd need to get the FTP site from me, but yeah, there's a description of it. I mean, there is a README file that kind of explains what every variable is. Well, part of the issue is there's no very standard way of distributing space-time cubes. Now, a lot of the people we work with use MATLAB, and so, I tend to just put it out there as .mat files, which has its own compression built into it and it works fine. Do you want a sequence of geotiffs? Do you just want a raw binary? So part of the question that currently why interacting with me is helpful is how are you going to ingest it, as well as what does it mean? And and in that case, we're sort of trying to, part of what we're doing is to try to find out what what's the logical way to do that for everybody.
Are there standard utilities for converting from one format to another?
Well, MATLAB reads geotiffs, it doesn't write them.
It's like going on a long chain.
Yeah. So the answer is yes, but they're not. The idea of how you furnish a whole sequence of space-time, a space-time cube is.
Take your microphone. You can keep on.
Oh, okay, yeah. you know, I don't know that, again, it's not.
For more, please visit us at stanford.edu.